let's move on to the next module. This is pretty short and a very simple concept, but it's very widely used in computer vision, not just computer vision, like a lot of other areas in machine learning. And this is called histogram. And I only have like few slides to explain this. So let's say you have this image shown on the left. Then what's going to happen here is, you know that you have like a certain set of pixels in this image, right? And each pixel has a grayscale value. Now, what histogram means is, first of all, this operates on the range of this image. Range means like, what are the values of these pixels? And what histogram represents is, it will just count how many times a grayscale value is occurring in this image. Okay, so that's a very simple definition of a histogram. Let me try to explain this using this example. So this histogram over here is like example, let's say coming from this image, and the x-axis over here, it starts from 0, which is kind of pure black, and you move towards the right, which is like pure white, which means that if you know the numbers, this indicates 0, and you will increase that number, and it's going all the way up to 255. Okay. Now, what this histogram is showing is how many pixels you have with value 0 in this image. And that's the number here represented by the y-axis. So y-axis is just giving you the count of pixels for each grayscale value. Okay, and that's it. That's called a histogram. There are a few important properties of histogram which are really, I think, important to understand. First of all, how you define this x-axis, and this is called kind of bins. So what basically you can have is, you can just have 2 bins in your histogram. And for example, let's say for grayscale image, what you can do is, if you create 2 bins, you will have to divide your range into 2 different segments. In this case, the range is 0 to 256. So you will divide it like from 0 to, let's say, 128, and then 128 to 256. So then that will have just 2 bins. And what's going to happen is, you will count all the pixels which have values between 0 to 128. That will be like one huge plot, or you can say like a bar. And the second bar will be how many pixels have values between 128 and 256. That's going to be a second bar. Okay, so if you think about this is kind of discretization of your range, and you can go like finer. The best you can do is, you can have 256 different bins. For each grayscale value, you can count like how many pixels you have. All right, so that's kind of variation you can have in your histograms. And by just visualizing this, you can say that, okay, you have a lot of pixels which are actually in this range, and very few pixels which are pure white, right? Because it's quite small number here, and this is pretty huge. And then this is kind of showing all the variation. So this is perfect gray color. You can see, okay, they are kind of there, but not like a lot. But again, a lot of black pixels, right, which are kind of darker. So that's what a histogram is. And as I said, it's a pretty simple concept. Let's like look at one more example, and then we'll move to the next topic. So this is the input image, and I'm just showing like 2 different patches from the same image. So this is patch 1, and this is the second patch over here. So for this particular patch, this is the histogram, and you can see that very bright pixels, we don't have a lot. Okay, most of the pixels are in this range, and most probably these are coming from the face. All right, and again, we have like some dark pixels which might be coming from the hair over here. Okay, and again, we don't have like completely dark pixels here. So this kind of shows you the variation of pixels or pixel colors or pixel intensities in this particular patch. In contrary, if you look at this patch, in this case, even without looking at this histogram, you can say that, okay, either most of the pixels are like completely white, or most of them are like very dark, right? And the histogram clearly shows you that. It shows you like all these pixels are close to white, right? These are corresponding to this white patch here. And you can see that nothing is gray. And these two peaks here corresponds to, I think the first one corresponds to the darker region here, and this corresponds to the darker region on the top. And you can see even with human eye, we can see the distinction, right, of these colors. And that's why we have these two different peaks. So this kind of help you in analyzing the image and extracting meaningful properties. In this lecture, we'll talk about image filtering. And this is the outline. First, we'll talk about how we can represent images as a function. And after that, we'll talk about how we can extract useful information from these images. And this will cover a histogram of images, how we can extract edges, how we can smooth noise in the images. We'll cover two important concepts, convolution and correlation. So these will be used for filtering. And again, these will be used later as well when we talk about convolution neural networks. Then we'll talk about image derivatives, how we can use to extract meaningful information from images. And finally, we will talk about some basic examples of filtering. Okay, so these are the chapters from these books. If you want to go into more detail of any of these topics, I will refer you to these books. So let's start with image digitization. Now, in the real world, if we are actually observing something, everything is continuous for us. We can't say that, okay, we are at the first pixel or we are at the second pixel, right? We can't actually divide it. And that's also true for if you think about if you are trying to measure something in real world. Let's say you have a scale. In a scale, it's kind of discrete. You can say that, okay, 1 millimeter, 2 millimeter, 3 millimeter, there's some precision there, right? But if you look at the objects in your environment, you can go in as much detail as you can. It's never going to end. So that's kind of continuous space. But as we move on to computers, we'll have to be discrete. We cannot capture these images in a continuous space. So therefore, what we have to do is we have to perform image digitization. And this is basically just transforming this continuous space into discrete space. And this image digitization, it has two main steps. The first one is called sampling, and the second one is called quantization. So we'll cover these two in detail now. First of all, let's try to understand this image digitization in a very simple one-dimensional space. For example, we have a function f, which takes as x as input, and it produces y. So it's a very simple one-dimensional function. Okay, so later we will see how we can represent images as function, but let's start with this simple case. If you describe this function in this two-dimensional coordinate space, and let's say this curve represents this function. Okay, so what's happening here is the x over here corresponds to the x-axis, and this is called domain of this function. Domain means on what values this function will operate. So this function will take values starting from 0, maybe this is 1, 2, 3, 4, right? So this is called domain of the function. And the output of the function, which is represented by y, that's called range of the function. And in this case, the y-axis represents that range. Okay. Now, as I said, image digitization, it has two steps, sampling and quantization. Sampling is discretization of the domain, and quantization refers to discretization of the range. All right. So let's try to understand how we can discretize these two axes here. So for example, this is another function f, and y is the range, t is the domain here. Now the first step, which was sampling, that was as I said, quantization of this axis. So what we do is, instead of having these continuous values, we pick certain values. So, and the value should be maybe we divide it based on some interval. So these values T1, T2, T3, T4, these are the discrete values which will act as range for this function. And converting the continuous space to these values, that's called sampling. What it means is this function then is only defined at these points. All right, you can't define that function between T1 and T2. Okay. Similarly, you can discretize the y-axis, which is the range of this function. And in this case, what will happen is, if you think about, of course, this function will be continuous, right? If it's a some equation which can be differentiable, it will be continuous function. So what will happen is if you use the value of P1, it will give you some value of Y, let's say at this location. Similarly, T2 and T3, you get these values. Now, what you do is you say that we are not going to use all the values in this Y-axis. We are only going to use some certain values. And what's going to happen is the values which this function is returning, we are going to round them off. And this rounding is called actually discretization. Okay. So that was a single like one-dimensional function. We can generalize that to two-dimensional function as well. And your images are two-dimensional function. And in this case, what's going to happen is you will discretize not just one axis, you will discretize both X and Y axis because it's a two-dimensional function. Okay, but it's the same process, but you have to perform on all the on both the axes. And similarly, like your range is always going to be like a single axis. Y, this vertical axis in this case, the process remains the same here. And if you try to represent that as like a matrix over here, what this means is you are dividing that continuous space into this kind of grid. Okay, so in this grid, your x-axis and y-axis, they will have only discrete values. Let's say 1, 2, 3, 4 all the way up to m, and 1, 2, 3, 4 all the way up to n. So these cells here becomes range of your function, and whatever value these pixels can actually have, they define the range of this function f. And again, we will have to discretize those values as well to complete the second step of digitization. And of course, we can extend that to 3D function as well. The only change here will be like instead of 2 axes, we'll have 3 axes here, and we'll have to discretize all those 3 axes. Now let's try to understand both the steps using digitization of this arc over here. So let's say we have this arc in this 2D space. All right. Now what we do is, so this actual arc is actually very continuous, right? So what we do is we create like this kind of grid where we have these steps in x-axis and let's say in the y-axis, and we can only have values at these cells, at the center, wherever like these axes are crossing. Okay, so the continuous curve was the original curve, but these blocks which I'm showing, this is the discretized version. Okay, and you can note here that like we are only assigning values when these axes are crossing. Okay, and if you just omit like this continuous curve, that you can still see like the digitized version. So that was sampling. Now coming to the second step, which is like quantization, what we do is we can only have, let's say, 2 values, 0 and 1. So all these like white spaces over here, all these have 0, right? Which means like the arc is not present. And wherever it's gray, that just say that, okay, arc is present. So we just store 2 values. But this arc might have like more than 2 values, right? Because it will the full range from 0 to 256. So that was an arc. This is actually showing a real grayscale image. And if you try to understand this, this axis and this axis is actually the grid, which is forming the image. And this is giving like the resolution of the image. In this case, it's 150 cross 150, which means like this image has 150 times 150 pixels. And this vertical axis over here is just showing you the intensity at each pixel. And again, this is kind of discrete because we can say that, okay, exactly like which grid cell in this range has like actually what value. And again, that value will be discrete. It will be coming from the range over here. Okay. So basically what we can do is if you have to define an image as a function, the rectangular grid, which I showed you in the last slide, that acts as a like a range of domain of that function. Let's say that function is P, and the values that function P can take is any of the grid cells. Okay, so it will be like X, Y coordinate, and then it will store like each grid cell will store a value, which will be like the range of that function, and it is called like the pixel value. Okay, that's how you represent your images in form of functions. And this is just exactly showing that. So this is your grid. And each of these like white circles over here, these are like your coming from your domain, which are like the representing the grid cell in this XY coordinate. And the grayscale value is actually the range, what value we are storing at that particular location. And again, that can have like some discrete set of values. So you know that we're talking about like the bit depth of an image, right? So that bit depth actually defines the range of your image function. So then this XY grid is kind of domain of that function, which you are using to define your image. And the values which these locations can store, they represent the range. Same goes for RGB images. It's just like instead of single channel, it will have 3 channels, and each channel will have a domain and a range. The domain is not going to change because all these 3 channels corresponds to like the same space. And again, the range will also be same most of the time. If it's 8-bit, it's going to be 0 to 256. Now let's try to understand like how sampling and this digitization actually affects the actual images. Now, the first step of digitization was sampling. So sampling will define what will be the resolution of your image. Okay, so if you're going to sample like at very bigger steps, which means that your image will have a very small resolution, let's say on the left. But if you're going to sample like very closely, then your image resolution will be very high and the quality will be very good, which is shown on the right. So sampling has a direct correlation with the image resolution. Okay, and if you think about this, your cameras has this metric, right? Megapixels, how many megapixels your camera can capture images at. So that represents the sampling rate. The second step, which is quantization, it actually indicates the quality of the image which you're going to see. If you're going to like create discrete steps at a distance, then it means that you are actually using a very low bit depth. For example, just 4 colors, you're going to see something like this. And if you are going to use like your discrete steps which are very close to each other, then you will get like a very high quality image. Okay, so these two are like both part of digitization, but they like correlate to different properties of your images. Now, there's another interesting aspect. Again, it's resolution, but it's different from the resolution which I told you, like the image resolution, which defines like how many pixels you have. It's called dots per inch. This has significance to like 3D, your 3D environment. Okay, and the idea here is you might have heard that your images has like, let's say 72 dpi or 300 dpi. This is kind of a norm, which means that if you measure the distance of like, let's say inch in a real world, then how many pixels that 1 inch will be. So this is also called resolution, but it's different from the resolution we were talking earlier. Right? So this will define like when you try to print that image, let's say in a paper, then what will be the quality? Okay, because this has like the real correlation with the actual distance in your 3D environment. Okay, so this DPI is dot per inch. It's saying over here, and this is entirely different from the sampling part which we were discussing. All right, so again, this is a simple example like covering all of those things, and this is showing you actually like how your pixels are actually discrete. They are not continuous, right? Because this is kind of a coarse scale we are using. And again, at each pixel, you can see that what value is being stored. And that value is again not continuous. So it's showing both the aspects at the same time. All right, then just one last point here. This is really important. So images are not just like images which you capture using your regular camera, right? Images can have different forms. And when we do computer vision, we might have these RGB, these normal natural images, but these are also like images. So this is, let's say, ultrasound, this is your MRI, and this is infrared, right? All these kind of different modalities of data can also be represented as images. So this is something to know, because when you are developing your algorithms, it's not going to be just operating on this kind of image. You might have algorithms or similar kind of algorithms which might also operate on these kind of images. Okay. Last lecture, we were talking about image filtering, and we talked about how we can represent an image as a function. We talked about like image digitization. And so today, moving forward, we are going to talk about image noise. Now, before talking about image noise, let's try to understand what each of these pixel values mean. And we'll try to do like a very simple analysis of images, the pixel values. This is called intensity profiles. On the left here, we can see we have our grayscale image, and we have drawn like two horizontal yellow lines. And on the right, you can see this is not this looks like a histogram, but it's not a histogram. This is an intensity profile of this image. What it shows is as you move from left to right on along like this yellow line, how the pixel intensity is changing. Since this is a grayscale image, each pixel value will have a value between 0 and 256 or 255, right? So you are starting from the left, and you can see like this was the pixel value. And as you move forward, you can see like it's dropping, increasing. So it's kind of fluctuating, right? And at this point, you can see like it's dropping a lot. And then it stays very low all the way up to the right. So if you look at the actual image, you will see that on the left, it's mostly clouds. So these are brighter pixels, right? And at this point, you can see like we don't have any clouds anymore. We don't have the clouds from this point onwards. And it's kind of sky. And it has to be blue if you look at RGB image, but it's in this case, it's kind of a darker pixel. And that's the reason like we are seeing this dip, right? And you can see that it continues because we have sky like all over to the end. Okay, so that's kind of intensity profile to understand how the pixel values which will change if you have different objects in your input image. Now, if you do like similar kind of pixel analysis on the second yellow line on the bottom here, so you will see that this curve was very smooth, right? It was not fluctuating a lot. But if you look at this intensity profile, it's actually fluctuating a lot. Still, it has a pattern because most of these are like dark pixels, and you can see that when we have this tree trunk, it's actually darker. So it's a huge dip here. But overall, you will see like it's kind of fluctuating a lot, and this one is kind of smooth. Now, if you look at the original image on the left, you will see that this object is kind of it has a very flat surface, right? The cloud, and in this case, it's ground, so it's grass, right? So you can see like the pixel value is changing a lot as you move across like neighboring pixels. Now, why this is important, you will later see that when you have noise present in your input image, it resembles more like this intensity profile, which is shown on the bottom here. So this is more related to noise, and that's why I showed you this simple example here. Now, let's talk about what image noise is. Now, first of all, before trying to understand what image noise is, why we see noise in image. So there are a lot of reasons for that. We can have like light variations. We can have noise due to camera electronics, how it was captured. There might be like some fault in the hardware which is actually used for taking that photograph, right? The sensors or the lens. It could be there due to like surface reflectance. It's not always uniform. It could be due to lens. There might be some dirt on your lens, right? Or the lens, the hardware itself might not be perfect. So a lot of other reasons why you have noise in your image, and noise is random. And one important property is it occurs with some probability, right? It won't occur like all the time. So there will be some probability associated with whatever noise you see in your images. And because it has some like probability, so it will have some kind of distribution. So if it has a distribution, what we can do is we can represent, like we can model this noise. And a very simple way to do that is, for example, if you have an original image which is completely noise free, right? We call this I original. And this is a function xy, you know that this is like these are the grid values. So this function will give you the true pixel value without having any noise. Okay, for example, this is the image. And then let's say at each pixel xy in that grid, we have some kind of noise, and we can represent that using this function small n. Right? So if we have to introduce this noise into this original image, the image model will look something like this. So this will be the actually observed image, what we will see. will have this original function, which represents like images without any noise. And we just add like the noise function. Okay, so this is one way we call this additive noise, because we are just adding noise to each of these pixels. We can have a different model where we can say that instead of adding, we can actually multiply noise. So that's called multiplicative noise. We can have varying kind of models. So let's not worry about like how it's represented, but let's try to understand like, okay, we can have this kind of model. All right. So this is the clean image. And let's say we had some noise, which was given by this function. And what will happen is you will see image like this. So this is like the observed image when you have noise in your sample. All right. So this is like the example of multiplicative noise, which I was explaining earlier. Instead of addition, what you do is you take that noise and you multiply that with the pixel value. And let's say if you have multiplicative noise, some function, then you will observe image something like this. Okay, so the most common form of noise can be represented using Gaussian function. We call this a Gaussian noise. Okay. And Gaussian function, you almost remember like from your maybe probability course, it's a curve like this, right? And this is like a very simple equation of Gaussian. From left to right, you will get these values. So this is kind of range of this function. And you can see that the maximum value of Gaussian is around 0, which is mean of this Gaussian function. All right, it peaks at here. And if you have like a Gaussian noise in an image, it might look something like this. But again, this will vary depending upon like what kind of Gaussian function you use. Okay, and the most important variable there will be this standard deviation. What's the standard deviation of the Gaussian function you are using? That will define what kind of image you are going to observe. So that was one kind of noise. Other ways to represent noise is like, let's say your noise is coming from a uniform distribution. Okay, so again, this is a simple function which says if your value is less than, let's say, a over here, if it's towards the left, your response will be 0. Right? The function will return 0 all the way up to negative infinity. And if the value of the domain is greater than b, all the way up to like plus infinity, again the function will return 0. But between a and b, your function is going to give this value. So it's kind of a positive response. And the positive response is only between a and b. And it's uniform because this value is not changing. Gaussian, you can see that from negative infinity, it was close to 0, but it was gradually increasing, right? Then it was peaking at the mean, which was 0, and then gradually going down. In this case, it's different. It was completely 0. So this is kind of a step function. Suddenly it's 1, or whatever this value is. So this is like 1 over b minus a to just normalize it. And then again, it goes to 0, and it will remain 0. Okay, so this is a very simple step function. And this is like also uniform distribution. And if we take like a noise from such a distribution, we call that salt and pepper noise. And the idea is like you will make each pixel in your image either black or white with some uniform probability. All right. So each pixel you will decide whether you will add noise or not, and then you will decide whether the noise should be like 0 or 1. So that will come from the step function. Either you will make it completely 0 or you will make it completely 1. So let's say if this is the original image, and if you have salt and pepper noise, it will look something like this. And you can see here that some of the pixels are like completely 0 and some are completely 1, assuming that the range of this image is between 0 and 1. Right? And other pixels, you won't change at all. The next topic is filtering, and I think this is more interesting than noise. So before talking about the actual filtering operation, let's try to understand some of the basic concepts of which will be required. So if you go by definition, image filtering is what you do is you take a function which is called a kernel, and you take like a small patch from your image, and you just compute like you can say like a linear combination of the function with the image patch, and that will give you some value. So it's kind of an operation which is performed using that kernel function on a neighborhood of an image. Okay, and this is like a very general formulation for image filtering. In this case, I represents an image. Okay, so M and N are like any particular like your grid locations in your image space. And what you do is you look into the neighborhood of that location, which is centered at M and N, and the radius of that neighborhood, that's defined by these two parameters, K and L. So how big that neighborhood will be. All right. And what you do is you have this filter function. You compute like a combination, or you can say linear combination of this function with the pixels in this neighborhood, and you do some kind of averaging, and that gives you like some kind of response. So this general formulation is called image filtering, where I is your image, F is your filter, and H is output, which is called like the filtered image. Okay, so M cross N are like the 2D coordinates in your image space. And again, K and L are like a 2D coordinates, which define like how big your neighborhood will be. Now, the question is, I think this is a very basic question, like why we need filtering. And later you will see like a lot of different applications of filtering, even in like when you try to study convolutional neural networks and deep learning, you will see like the basic operation which is being performed as filtering. So that's one thing. But other than that, like that's more recent. In earlier days, people used to use image filtering for enhancing images. It could be if you have noise in your image, which you just looked in the previous set of slides, right? There will be noise in your image. So how to remove that noise? If you have to perform resizing of your images, then again, filtering is used. And if you have to perform like different kind of operations, for example, if you want to increase or decrease contrast or any other image manipulation, filtering is very useful. Okay, so that's one use, which is called image enhancement. Then the second is like if you want to extract some meaningful information from images, then filtering is very important. And this correlates to like when I was talking about how filtering is used in deep learning. So we use filtering to extract the useful information, which is used for making predictions. Okay? So this information could be either like texture present in the image, it could be edges, it could be like distinctive points, and many other interesting features. And again, you can use like to detect some patterns, and this also correlates to extracting useful information. You will see like how these two are very related to each other. And for detecting patterns, template matching is like one interesting use. And I think in the first lecture, we were talking about how we can use template matching for object detection. So we're trying to detect patterns, right? And there, if you remember correctly, we were using correlation. So that correlation is actually a filtering operation. All right, so let's see like a concrete example of filtering. Now on the left here, I'm showing you a very small patch of an image. So your image will be pretty huge, like it will have a lot of pixels, but let's just focus on a very small neighborhood of that image. And in this case, it's just 3 cross 3. And these are pixel values. Let's assume that it is a grayscale image, and these are the pixel values. Right? So, and in this case, you can see like the neighborhood is like neighborhood is 3 cross 3, and we are interested in this location. This is like the X and Y where we are centered at. And FP, let's say, is your kernel, okay, which is operating at this point P. Now, what will happen is when you apply this filter on this neighborhood, what this function will do is it will utilize all these values in some way or other. Right now, we don't know how it's going to utilize, but it will make use of all these values. And after doing that, it will come up with a number. Okay. And that number will replace the location which we are interested in. So this step is called filtering. So how these numbers will be utilized? There are many different ways that differentiates like different filtering operations, but that's like the high level how filtering is performed. Okay, so let's try to understand from a concrete example of a kernel. In this case, this is an image patch. Again, this is 3 cross 3. And in this case, the function f I was showing you earlier, in this case, it's a 3 cross 3 kernel. And these are the values. All right, so don't worry about like how we estimate these values or what this kernel is. Right now, just try to understand like how this filtering operation is being done. Okay, so just try to understand like the computation part of that. So what we do is we take this image patch, we take this kernel, and we just compute a linear combination of the values in this image with the values present in this kernel. And a simple way to do that is you can just perform element-wise multiplication of all these values and then sum up all those values. So if you remember this, like from the linear algebra basics, this was called like Hadamard product, right? So this is like you perform Hadamard product and then you will just take average of those values. So it's a one step like ahead of that. And you will just replace the value of this pixel with whatever value you have obtained. Okay, so in a way, I mean, this is also a linear combination because what you're doing is you are taking a linear combination of all these pixel values. And to take that linear combination, you are using the values in this kernel as weights. So if the value at a kernel is 1, which means that you will give like importance of 1 to this pixel value because you're multiplying this with 1, right? So if you look at this value, you are saying it's 0. It means you don't want to pay any attention because this is going to multiply with this and it will become 0. So you're ignoring this pixel value. Similarly, you are ignoring this pixel value. So if you try to visualize this kernel, what's happening is all the pixel values on the left over here, they are being given like equal importance, right? This will result in like 1, 2, and 4. And at the center, not that much. You're just paying attention to like the center pixel maybe, but very small amount. And again, you are paying attention to the values on the right, but like the negative side, because all of these are negative values, right? And this will make all these values negative. Okay, we'll discuss more like the interpretation of the kernels. But basically, you just do element-wise multiplication, take average, and replace the pixel value. So this is like one filtering operation. Now, there are different formulations like which you can use to represent this filtering. And the basic one is called correlation. And the mathematical formulation for correlation is you have two different functions, f and h. And what you do is you perform like element-wise multiplication of these two functions over some neighborhood, like in this case, like k and l, if it's like two-dimensional function. And correlation is used to find out if two different functions are similar or not. And this you have seen in the first lecture when we're trying to perform object detection using pattern matching. If the patterns match, then we get like a very high response, which means the correlation is very high. So this is directly coming from statistics. Okay. In this case, what we do is if we have to use correlation to perform filtering, we represent the first function as image and the second function as kernel. So first function becomes something like this. The second function becomes this. So there's the image patch. This is your kernel. And the operation, if you go through like steps of this equation here, it's nothing but the steps I explained to you in the previous slide. You just perform element-wise multiplication and add those values up. All right. So that's correlation. The second way to represent filtering is convolution. And you might have heard of convolutional neural networks. We're going to study that in this course in very detail. Now, convolution, the mathematical formulation is almost same as correlation. We have two different functions, right? And again, we look into some neighborhood like of these functions. The only difference is we flip the second function. All right, so because we have these negative values. In correlation, this was all positive. And again, it's the same representation, f is image, h is kernel. Now, if you have to represent convolution in form of correlation, what you can do is you take your kernel, because you have negative values, you can actually flip it in both the axes, x and y. So in this case, we are flipping like along x-axis. So this becomes positive. Then we can flip along y-axis, then that will become positive, right? Then it's exactly same as correlation. So let's say this was the initial kernel, you flip along x, flip along y, you get this kernel. And then again, you can just perform correlation of this kernel with the image patch. It's the same equation. Okay. So you can see like correlation, convolution, exactly same thing. The only difference is the kernel values. Now convolution, like it's associative. These are some interesting properties. So we can quickly go over these. So associative means like if you are performing convolution of G and I first, and then convolving that with F, it doesn't matter like what order you use. You can actually first convolve F and G, and then convolve the result with the second function. Okay, so it's associative. Now, just going over the definition. So convolution, it's like a filtering operation. So is like correlation. And so convolution is kind of giving you how much is the overlap between two different functions. All right. And we have the negative sign, which means that we actually shift the we shift the kernel over our function, and we try to find out like if there is some overlap or not. But the high level intuition remains the same, because correlation is also comparing two functions and finding out whether they are similar or not. Okay, so the basic idea remains the same. Now, before going to like the actual some of like, we'll go through some of the examples to perform filtering. There are like two other concepts which are very important. We'll see. So first is mean, and you all must know this already. Mean will be like you have different values, and you add those values and divide by the number of values, right? So it's a standard mean. And again, I could be just a number, it could be a matrix, it could be a vector, anything. Right? Now, an advanced form of mean is weighted mean, which I think is more relevant to us. And this weighted mean is also related to, we have been talking a lot about linear combination. Okay, so if you look at the numerator of this equation over here, this is a form of linear combination of all these values, right? And these W1, W2, all these are weights. The only difference is you normalize this value. Okay, so basically when we will perform filtering, we will see that most of the time it's going to be linear combination like this. And we are going to normalize with like the number of pixels we are actually operating on, the size of the neighborhood. So this is actually showing the filtering operation which we are going to use. Any questions?
I have a question. In the function, we're talking about G, right? When doing the convolution operation, what does the associated property, what does the G represent?
G, it could be any function. It could be any function. In this case, we're interested in images, so we can say G could be an image. But in general, it could be any function.
Right? Or can be a function, or can be a kernel.
Yeah, it could be a kernel as well, because it's kind of commutative as well, right? It doesn't matter whether you represent G as image or G as kernel. Yep. I could be image, or the result will not change.
I have a question. So in the flipping part, where you like differentiated the convolution and this one. So here, like you said, minus k and minus l, multiplying it with minus k, like minus, is it like a horizontal and vertical flip? So I couldn't really understand like how multiplying a value with just a minus value is also flipping it. I mean, we are not flipping it, we're just not multiplying it with minus. So like for example, h1 should be minus h1, right? So the value here, whatever the value is.
Right. So, yeah. H7 will be your negative of h1. So these k and l, these are not actual values.
These are indexes. These are indexes.
Yeah, these
right?
are indices. Right?
Oh, yeah. I see. I get it. Yeah.
So think about like if you have a coordinate system, right? You're going from negative x to plus x. So you just flip the x's.
Yes. Okay, that's good. Thank you.
What do you mean convolute another convolutional kernel, like the f times g times the I? I understand using the kernel to apply to the image, which is just like which is just applying every grid applied to them and then just sum them together. But what about the f times g when f convolute g when f and g are both convolutional kernel? Isn't that you just end up with one grid?
Okay, so in this case, let's say I is your image. Okay. And let's say, and again, this is just one example. I mean, we can have like a lot of other variations here. Let's say I is your image patch, G is your kernel, first kernel, and F is your second kernel. So we want to perform filtering on the image, let's say twice.
Yes.
So then you will perform filtering on I using G. You will get some result. And whatever result you have, you're again going to perform filtering using F. Right?
Yeah,
so
I
that could be one
understand.
interpretation.
Yeah, I understand applying the G first, then applying the F. But what about the right hand side? Apply the F to
Right.
the G.
Yes.
That's
Okay.
where I
So,
confused.
all right. So whatever result you get using this operation, even if you just perform convolution of the kernels first, that will give you just one kernel. And if you use that kernel to perform filtering on image, the result is not going to change.
Yeah, I understand that it won't change, but I just couldn't figure out how to convolute how to convolute two kernels. Because for example, if we have a 3x3, right, then we just only update the center one, which is a 2 pixel, right? If it's a 3x3 image, then
Right.
how we going to do that if we have two kernel? Is that the same? Then we just end up with a new FG kernel that only change the 2 position. Then we use that new FG kernel applied
Yeah,
to
that's a very good question. So we'll have an example later on. We'll talk about that. Okay, just wait.
Okay.
Okay.
Professor,
Yes, go ahead.
in the filtering slide, I couldn't understand how the filter output was 5. Like, can you show show how the calculation is done?
This
Yeah,
one.
this one.
So these are all 1, right? So this is
Yeah.
going to give you 6, 7, right? If you sum up all these values, 4, 5, 6, and 7.
Yeah.
And
So
10 times 0.1 is going to give you 1. So that becomes 8.
oh, so we are
And
multiplying all.
okay, so let me go over again. So this one has a weight of 1. That will give you a 1.
Yes.
2 will give you 2. 4 will give you 4.
Yeah.
This becomes
Yeah.
7. That's
Yeah.
true.
Yeah.
These two become 0.
Yes.
10 will become 1.
Yeah.
So you can add 1 to like 7. That gives you 8.
Oh, so
Okay.
this is not a multiplication. It's a convolution sign. So it's just one number. I was thinking if it was a matrix multiplication. Okay, got it. Sorry.
Okay. All right, good. I think there is another question. How can we define kernel values? That's a very good question. And that's, I think, a major portion of this course, how to learn these kernels. We'll talk about that when we start going through convolutional neural network. And I will also show you some other interesting examples of these kernels. Okay, but that's a good question. So we will talk about like how to come up with values for these kernels. Any other question before we move forward? All right, good. So the next topic is we'll just we studied like how to perform filtering. Now we're going to go over some of filtering examples and really see like what filtering means in images. Now before doing that, let's try to understand some basic filters. Now the first one is Gaussian filter, and Gaussian filter, this curve you have seen before. This is a Gaussian curve. All right, it's symmetric across the mean value, and towards the left it becomes 0. Towards the right it becomes 0. So it gradually decreases as you move away from the mean. And this is the equation for this Gaussian kernel. So this is one-dimensional. What you can do is you can also have like a two-dimensional Gaussian function. If you try to visualize that, it will look something like this. Okay, so it peaks at the mean. In this case, the mean is like two-dimensional 0 cross 0, the origin of the plane. And again, same to like this 1D Gaussian kernel, it's also decreasing. If you look like at this, yeah, we'll take questions later on.
Okay.
So if you look at this Gaussian kernel from the top, we can actually represent that as a heat map, and the heat map will look something like this. Okay, so what this means is the black value represents completely 0, and the white represents a very highly active value. Right? So you can see that at the center, which was pretty high, we have like it's a high value here, right? So that's the center of this Gaussian. And as we move like towards the outer boundary, the value is actually reducing. And you will see like why this representation is useful. We can create like a two-dimensional kernel using this kind of visualization, where the center value in the Gaussian kernel will be very high, and the values which are far away from the center will be very low. All right. So this two-dimensional Gaussian, again, it's the same equation. Again, you will have just two axes for this. Now, looking at the one-dimensional Gaussian filter, so what we do is we take this Gaussian curve and we discretize the values to create the kernel. And here you can see that this is the center of the Gaussian, and it's 1, which is kind of like the maximum value we can have. And you can see that as we are going towards the left, the value decreases. So we are at 0.6, 0.13. It's almost going to 0. And if we move towards the left, it will be almost 0. And again, if we go towards the right, we can see like it's kind of symmetrical. That's a property of Gaussian. So the values won't change, but again, they will reduce and again, gradually becomes 0. So this is like a discrete Gaussian 1D kernel. Now, similarly, we can form like a two-dimensional kernel for Gaussian. Instead of a vector, it will be a matrix. And again, we'll have a very high value at the center, and the values will gradually reduce as we move away from the center. Now, why Gaussian is this important? So you will see like Gaussian is coming up again and again when you have like your statistics course, right? In your probability course, you might have seen this a lot. So one simple example, like the plot I'm showing here, even in the class, like if we take like all the female students, right? And if we will try to measure like the shoe size for them, you will see that if you try to plot a histogram for that, it's going to be a Gaussian. Okay, this is just one example, but if you take like enough number of samples, it will look exactly like a Gaussian. And this is not just true for like female shoe size. Even like in the class, if we just measure like the height of all the students, it is going to be a Gaussian. And most of the times, like the grades we receive, it's very close to Gaussian. Very hard to get at a Gaussian curve, but most of the time it's kind of a Gaussian curve there as well. Okay, so it's like it's a distribution which is it's very natural, and you will see like in your 3D environment all the time. Okay, it's like the most common natural model. And there are a lot of interesting properties of Gaussian function. So first of all, it's a very smooth function. It's symmetric. And again, we'll talk about derivatives later on, why derivatives are important. So one interesting property of Gaussian curves is like you can keep computing derivative of that function, which I was showing you earlier. It's going to be Gaussian every time. Okay. So, and again, if you compute Fourier transform of Gaussian, it's going to be Gaussian. We'll briefly cover this aspect in, I think, one of the lectures. And if you compute convolution of a Gaussian function, like convolution of two different Gaussian functions, again, you will get a Gaussian function. And this is really important property. We have a lecture on this where we will use like to extract some meaningful features using Gaussian filtering. And this property is like, if you have a 2D kernel, which is, let's say, if it's a Gaussian, then we can perform that 2D convolution operation as two independent 1D convolution operations. And the reason we do that is like 1D convolution operation is very efficient. We'll talk about that as well, so don't worry about it right now. But it's a very interesting property of Gaussian. And this is again just a fact, like we have cells in our eye that actually are performing Gaussian filtering. So earlier we were talking about how noise is introduced in images, right? So then I was saying, what's the true color? And there were a couple of questions. Again, even if we know the true color of, let's say, an object, a chair, right? But again, what we are observing, there can be like a lot of noise in between how we are observing it. Again, it could be like the lighting condition, the light might be very dim, there might be some dust in air, right? So there is natural noise present there, and we have this Gaussian filtering going on when we form this image in a retina. So that filtering operation is being performed to denoise that image. All right, so let's talk about some interesting filtering examples. Now, this is your input image. You have seen this image a lot. So we are going to use this separately in this course. This is a very famous like Lena image. And in this case, this is our kernel. Okay, so you can see the kernel is like all zeros and it's 1 at the center. Now, I mean, most of you can easily guess, like if we have such a kernel and we perform filtering using this kernel on the input image, it won't change anything. The image will still remain the same. So if you try to visualize this kernel in two-dimensional, it will look something like this. The center is pretty high and all the other values are 0. And the reason it's not doing anything, because if you try to use the neighborhood values, it's saying everything is 0. So it's kind of enforcing that you don't use anything from the neighborhood values. Just use whatever you have at this particular location. And if you do that, it's kind of, you are not changing the image. So it won't change anything. All right. So again, but this is a filtering operation and this is a kernel. Now let's see some variation. Let's move that one towards the left. All right. It will look something like this. So don't worry about the orientation of this plot. It's just saying that, okay, now the weightage is being given to like a pixel, which is like neighboring of this, the pixel which we are interested in. Now, I mean, you can perform the filtering operation, which we discussed the equation, but if you try to think intuitively what's happening here, what we are doing is we are actually not using any of these values, right, in the neighborhood. And we are even not using the value itself in which we are interested in. But what we are doing is we are using the value which is on the left. So if we, Teja, can you please mute your mic? So if we use this value, then essentially we are actually taking this value and storing at this location. All right. So now what will happen is your image will shift. And you can see that since you are moving values from left to right, your image is going to move from left to right. It's just a shifting operation. So now you know that, I mean, using this kind of kernel, you can actually perform shifting in your images, which is very interesting because this is a very simple kernel, right? Similarly, you can actually have one at any other location and you can perform shifting. For example, if you have one over here, it means that you are shifting the image diagonally. Okay. Now, this is another interesting kernel. And in this case, what's happening is we are actually paying equal attention to all the pixels in this neighborhood. Right? And you can see here that we have this normalization factor, and that's due to like we don't want to mess up with the pixel values, right? So we want it to be normalized. And the normalization is coming from summing up all the values in this filter. Earlier, we didn't need this because we just have 1. So if we divide by 1, it won't change, right? Usually we normalize our filter. So we have 9 different values and the kernel is actually normalized. In this case, what's going to happen is you're saying that if you're focusing on this pixel, please also look at all the other pixels in the neighborhood. All right, so let's see what's happening. It's kind of smoothing your image. So this is in a way like you can say a blur filter or a smooth filter. So it will smoothen your image. Okay, later we'll see like how this is useful. This is another example of the same blur filter. In this case, a filter is slightly bigger. This was a 3x3 filter. In this case, it's a 5x5 filter. All right, and again, you can see the normalizing factor. It's 25 because all of these values will sum up to 25. And again, you can estimate that what's going to happen. This is going to smooth your image. But if you compare this smoothing with the previous one, this is like much higher smoothing because you are considering like a bigger neighborhood. Right? In this case, it's 5x5. Earlier it was 3x3. You can keep improving the increasing the size of the neighborhood, and then your smoothing will keep increasing. Okay, so that was like a very simple smoothing filter. Let's talk about Gaussian smoothing. So this is a Gaussian filter, and you can see that the center of the kernel, it's pretty high. And as you move towards the neighborhood, the values are going down. So this resembles like a Gaussian kernel, but it's kind of a discrete form of Gaussian function. Okay? Now, again, if you perform like filtering using this kernel, you can see again, it's kind of smooth, but it's not very distorted. You can say like it's not that bad when you're filtering using like all ones. So this is slightly better than the previous filter. And that's one of the reasons why Gaussian filter is used in filtering. And the reason for this is you can see that whichever pixel we are focusing to, we are actually giving more weightage to that pixel. And as we move away into the neighborhood, the weights are going down. So it kinds of say that, okay, you're not completely ignoring the neighborhood. You are still using those values, but not that much. Okay. Now let's try to compare the smoothing operation using Gaussian and using averaging. So this averaging is like the filter which I showed you earlier, where you had like all ones. You are giving equal weightage to all the pixel values. So this is Gaussian smoothing, and this is smoothing by average. You can see like this is much more better than this image on the right. Now let's try to understand what will happen if we have noise in our image. Okay, so the original image which I showed you earlier, we try to add like some additive Gaussian noise, and don't confuse this Gaussian noise with Gaussian filter. Gaussian noise is something which we discussed like earlier in the lecture, right? Again, it's coming from Gaussian distribution, but we are adding those values which are coming from the distribution as a noise. Okay, so we have this image which is noisy. If we perform average filtering, we'll get something like this. And if you perform Gaussian smoothing, we get something like this. So I mean, it's hard to say which one is better. But again, in this one, we are kind of losing the texture, right? We are smoothing the image a lot. But in this case, we are getting rid of noise, but it's not that great. But still, we are not losing the fine-grained information which is present in the image. Okay. Now, another interesting filter is box filter. This we have seen earlier as well. So what it will do is, as we discussed, it will just replace like each pixel location with average of its neighborhood, right? So let's try to understand that on this example, because earlier we couldn't understand what really is happening. So this is a more concrete example here. Let's say this is an image patch, and so all the dark pixels, these are all 0. And we have like some bright pixels which have value of 90. All right, so let's say this is your image patch, and let's perform filtering using this box operator or box filter. So what will happen? You will first place this filter at this location, right? And you perform filtering. What's going to happen? You will get all 0 because all these pixels are 0. Right? Then this will be the next location. You move like towards the right, and here you can see like all of these are 0. This is 90. So if you take like average, it's going to give you 10, right? Because all the other locations in the filter will become 0. Only this will give you 90. And if you divide that with 9, that's going to give you 10. And you can keep doing that for all the locations. I'm not going to go through all of that. Let's talk about like at this location. Okay, so these three on the bottom row, these are all 0. And this is also 0. So if we just try to like a quick math here, we have 4 pixels which are 0, and we have 5 pixels which are 90, which means this is going to give you like maybe 10, right? Because, okay, hold on. So you have 3, 4, 5. That will be 450. If you divide that with 9, yeah, 50, right? So, okay, so you just add these values. This will be 450. Divide by 9, that's going to give you 50. Okay, so this is you can see like a missing pixel. Then you replace that with the average value. At this location, what's going to happen? I mean, the values won't change, right? Because all the neighborhood, it's the same set of values. Everything is 90. So it will still be 90. So now you can see that how the smoothing operation is being performed here. You will see like at the center of this region, the values are actually not changing a lot. Most of these are still 90 because the neighborhood was 90. So again, same is the case with like where you had all zeros. But the effect is like when you have a boundary, when you're moving from 0 to 90, right? You have an edge. There you will see that your filter is actually performing this smoothing operation. because these values are changing. Okay, and this is deliberately put there. So this is a 90, and you can see this could be an outlier. Now, if you perform smoothing, you can see like this reduced to 10, right? So in a way, if you use box filter, you're actually getting rid of these outliers. So this outlier is not present in this filtered image. All right. So this could be like noise or something, which is removed by this filtering operation. All right, so what it's doing is it's smoothing and it's trying to remove sharp features. For example, if you have edges, it will smoothen the edges. So this is like a very extreme case of box filtering. You can see that like all these sharp features, they are completely gone after box filtering. All right, so this is, you might remember like this eye of a very famous like scientist. And now you know that you have this filter, if one at the center, not going to change. If you have one on the right, you know that the image is going to shift towards the left. Now there was a question like the use of multiple kernels, but still we are not there yet, because this is not like a filtering operation. So this is your first kernel, which is kind of saying that, okay, give more weightage to the center pixel. All right, and this is like a smoothing operator or a box filter. Again, trying to normalize this, and you can see that it's 2, because if you try to normalize like all the values or the resultant values, the sum will be 1. Okay, so it's still like a normalized kernel. So this is a very famous kernel, and this performs like sharpening operation. This is called sharpening filter. Okay, so you can see that this image, it was kind of blurry. So this filter is actually bringing back the edges. Okay, and the reason is because it's paying more attention to the center filter itself. All right. So that was the original image, and if you perform filtering using that filter, sharpening filter on the whole image, we'll get something like this. You can see that like all the edges, like in the code here, they are recovered. So this is much better image than the left. All right, so more examples of filtering, and this is, we are moving more towards like extracting important features in images. So far we have seen like how we can perform smoothing operation or maybe remove noise. So this is a very special filter. This is called Sobel filter. It's used for detecting edges in your image. And if you use this for filtering, you can see you will get a result something like this. And what this is showing is, this is kind of showing all the vertical edges present in your input image. Wherever you have a vertical edge, you will get a very high intensity at that pixel location. Similarly, you can, so this is like the edge detection in the vertical direction. You can just rotate this. And again, this is part of a Sobel filter. In this case, we are trying to detect horizontal edges. Okay, so don't worry about like if you don't understand how we are getting horizontal and vertical edges, because we are going to cover that when we talk about derivatives and all that. Okay. So if you perform filtering using this filter on this image, you can see like all these are the horizontal edges present in the input image. Okay, so some key properties of linear filters. If we add the filters, that's similar to like if you perform filtering on the first and then add later. Okay, and again, it's kind of shift invariant, which means that it doesn't matter like where your pixel is located, the output is not going to change. Okay, so you can shift your image first, perform filtering, shift back again. So shifting is not going to change your output. And this is important because if you have an operator which is linear and shift invariant, you can represent that as a convolution operation. Okay, commutative, I think this property we have, oh, we didn't cover this again. So yeah, it came up. The issue is like, we were talking about one is kernel, one is image, right? And I said, it doesn't matter. You can have like this as image or this as image, the result is not going to change. So that's the commutative property. Okay. So you don't differentiate between your filter and your signal. Signal in this case is your image. Associative, we have seen this before, so that's good. And again, so this is also interesting. We saw one example for this, and this goes for the subtraction as well. So if you consider this as a filter, so you're adding two different filters and then perform filtering, the result is not going to change if you perform like filtering independently and add the result. Okay. The other interesting operation is about scalars. So if you are like scaling your image, it doesn't matter whether you scale first or you, let's say, you can even scale your kernel. That's not going to change it. All right. In this case, let's say you are scaling your image. In this one, you're scaling your kernel, and in this case, you are performing filtering first and then scaling the result. So all are similar. So this is identity operation, unit impulse. I think we saw one example of this when we just have one at the center. So this is one-dimensional kernel, but you can have two-dimensional kernel where you just focus on the center one. So your result is not going to change in that as well. All right, so I think this one should be the last one we cover today. And this is called median filter. So median operation, I think you should all know from your basic maths. All right. So what median filter will do is, in that neighborhood, instead of computing average or any linear combination, it will just select like the median value. All right. So we'll see like what are the advantages, and it's not same as convolution because we are not actually using the neighborhood values. So let's look at this simple example. I think it will be more clear. So in this case, when you are using mean filter is like you have a one like at all the places, right? It's normalized, and we know it gave you 50. Okay, what if we use like a median filter? Now median filter will actually take all these pixel values in the neighborhood. So we just have 0 and 90, and it will pick the median value. And in this case, you can easily see that you have 4 pixels which are black, 4 pixels which are white, or sorry, 5 pixels which are white. So definitely the white pixel is the median. All right, so the value will be 90 if you perform median filtering. Now, let's look at the example and try to understand like why median filter is better. So on the y-axis over here, this is just showing you the shape of the kernel. Right? So this is 3 cross 3, 5 cross 5, 7 cross 7. You are gradually increasing like the neighborhood of your kernel. And on the x-axis here, we have like different kernels. We have mean filtering, Gaussian filtering, and median filtering. So generally, you can see that as you increase the neighborhood of the kernel, your Gaussian filtering is actually doing a better job as compared to mean filtering. But if you look at the median filtering, even with like 3 cross 3 kernel, it almost removes like all the salt and pepper noise we had in this input image. Okay, so if you think about this, why that's the case, in median, we actually don't care about all the values which are present in the neighborhood. We don't perform any averaging. We just pick the median. So in that sense, we are not changing the pixel intensities. So it's not performing any smoothing or that kind of operation. So it's just like picking the value, which is like the most prominent in that neighborhood, and just using it. And because it's like coming from the actual image we had, so the quality is pretty good. Okay, so now one drawback of median filter is if you think about this, mean filtering, Gaussian filtering, whatever you do, it's a linear combination. So the computation cost is not that high. But in case of median filtering, to get that pixel value, you will have to first perform sorting, right? So you'll have to take all the values in that neighborhood and perform some kind of sorting to get the median. And that sorting operation is actually computationally expensive. And that's why we don't do median filtering. Now, another important point, I think, when you solve your programming assignment on filtering, this will come up. What should be the size of your kernel? All right. And there's a very simple rule of thumb for Gaussian kernels. Whatever standard deviation you have, you just set like half width of your kernel to 3 standard deviations. Okay. So the intuition behind that is, for example, you have this green Gaussian kernel. All right. So this is kind of a thicker. Thicker means it has a bigger standard deviation because the values are deviating a lot. And if it's like a very high peak, for example, like this blue over here, it means that it has a small standard deviation. All right. So what happens is you don't, of course, want like a very big kernel which has all the values 0. Okay. So what we try to do is we try to clip at this location where the Gaussian curve is actually going close to 0. And that value actually turns out to be 3 sigma. And that's why what we do is we take 3 sigma here, 3 sigma here, and we just discretize this curve. And that will give you your Gaussian filter. And the same holds true even if you have a 2-dimensional kernel. All right. Now, another interesting question is like what happens if we have edges, because we can't place your kernels on the corners. And there are many different solutions to that, and we should actually not worry about that. So we can actually extrapolate those values. We can actually even just make them all 0. Okay, that's called clipping filter, something like this. This is your smoothing filter. You can wrap around, which means that you can rotate the values, the pixel values. You can consider that this was like a cylinder, right? And what will happen is your values will navigate from right to left and maybe top to bottom. Okay. Then it will look something like this. And you can see that it's happening because the pixel values were being propagated from this right edge to the left edge. And you can see that the pattern is actually exactly like this. And that will be the filtering operation. You can actually copy edges. And that's actually also easy. You can just extrapolate the pixel value towards the right or top or left. Okay. It will be something like this. You can see like the values are actually just extending. Okay. And there are many other ways, like you can do all that. So all that is fine. Let's start. Last lecture, we were talking about image filtering, and we covered several concepts which are important to understand this fundamental operation in computer vision. Today, we are going to continue that, and we'll talk about image derivatives. Now, derivative, this is again coming from your high school maths. So if you remember like the definition, derivative just gives you rate of change. All right. And again, it can have various different meanings depending upon the context. A simple interpretation could be, if you have a function, then if you compute a derivative on that function, it might give you like at any point in that function, the slope of that function, right? And if you look at like your day-to-day life, if you're, let's say, driving a car, then again, if you try to compute the derivative with respect to distance, with respect to time, you will get speed. Again, if you try to compute derivative of speed with respect to time, you will get acceleration. So that's real world interpretation. The simple formula to compute a derivative is shown over here. So let's say you have a function f, and it's defined over a domain x, which is the values which this function will receive. So if you take a very small incremental step in this axis, in the x-axis, right, then you assume that that step is very small, and then you observe how much the function response is changing. All right, so that's what is being shown the numerator of this function. So fx will give you the value of this function at x, so x could be anything. And then you change this value of x with a very small amount, which is like, you can say the limit goes to 0. And again, you try to observe the response of this function. And then you take a difference between these two, which says that how much the function is changing over this very small interval. And then you try to normalize that using this interval. So this will gives you like how fast your function is changing. Okay. And as I said earlier, this is also like, you can say, what's the slope of this function at this point? So this is represented as f, this single dash over here. And you also use like a subscript x to represent a single derivative. Okay. Now let's quickly go through a few very simple examples. Like you might have a function, something like this, x squared or x times 4. You add these two values. And again, this is high school maths, just a recap. All of you should know this. And you can compute derivative of its function with respect to x, which is represented as dy over dx. And we have the formulas. Again, we are not going to go over those formulas. This will gives you like 2 times x and 4 times x cubed. Okay. Similarly, you can compute like derivative of other functions. In this case, it's not just like function of x. You can have like a sine function on top of that, or you can have a cos function on top of that. And again, these are coming from like the formulas which you might have learned in high school. So a derivative of sine function gives you a cos function. And if you compute derivative of an exponential function, it gives back you exponential with the sign which you are using like in the exponent. Okay. Now, this derivative has like it has a continuous meaning. So you can compute derivative only if a function is continuous. But there is a discrete form to it. And this is like the exact same form which we discussed in the last slide. So in this case, the idea is this x can have like a discrete value. All right. So it doesn't have to like, the limit doesn't have to go to 0. So what we do is we say that that small step is actually 1. This is the smallest discrete step you can take along the x-axis. And then if you replace this delta x or that small step with this value 1, the numerator will be just like fx minus fx minus 1, right? Which means that that's the smallest step you can take in this direction. And when you take that small step, how much the function value is changing. So that will be the discrete form of derivative. Okay. So you can ignore the denominator here because it's just 1. So it just becomes difference of the function value as you move forward. So essentially, like it's just like the amount of change you are observing in that function. You can represent that as derivative of the function at that particular step. Okay, so there are different forms of this discrete derivative. And again, so these are just definitions. Somewhere you might find like the definitions are different for like backward and forward, but it actually doesn't matter. We'll see later when we use this for filtering, then it doesn't matter whether we are using backward difference or forward difference. The result is not going to change, but this is just for understanding. So backward difference is when standing at any time step, you compute the difference with the previous step. All right. So x is the value like where we are standing right now in that function, and we subtract that value with the previous step. So we go 1 down towards the left, right? If it's like the x-axis. So that you can say backward difference because you're subtracting like the previous value. You can also compute like the difference with the next step. So in this case, it's x plus 1. This is called forward difference because you're subtracting like the next value. All right. So if you think about like x is kind of a parameter here, right? So it doesn't matter like whether you do fx negative of fx minus 1 or fx minus fx plus 1, because I mean, essentially you can get same values depending upon at which step you are computing this derivative. And this is another interesting case, which is called central difference. In this case, what we do is we actually, if we are standing at a location, we don't use the value of that location. We just look the value of the next location and the previous location. So in this case, we'll take the value at the next location, which is fx plus 1, and subtract this with the value at the previous location. So this is called central difference. Okay, so these are just basic definitions. As I said earlier, somewhere you might see that this is called backward difference and this is called forward difference. So don't worry about that. It's okay. Now let's try to compute these finite differences in some concrete example. In this case, fx is a function. It's a one-dimensional function, and these are like different values at different steps. Right? So it's going from 10, then 15, 10. So the value is changing. And you can consider that as we are moving from left to right, we are actually moving in the x dimension. Okay. So if we compute finite difference, then what will happen is, let's say we compute the backward difference. So at this location, we don't have any value on the left. So we can just ignore it. So we start from this location, you subtract the previous value, that will give you 5. Again, you will compute backward difference at this location. So you subtract this, that will give you -5. Again, you do for this location, 10 minus 10 will give you 0, and you can keep doing that. So this second row over here is actually the first derivative of this function fx. And we computed that just using the finite difference, right? Similarly, you can again repeat that process on the first derivative. So in this case, you can see like this will give you 5, this will give you 10, and you can keep doing that again. Just repeat that, computing the finite difference. And this is again derivative of the first derivative, and we call that the second derivative. So if you look from like from the perspective of the original function, this is second derivative, and we can keep doing that, get like third and fourth derivatives. Now let's see if we can do like slightly better than this, and instead of like subtracting these values, can we create derivative mask? And the idea is, since we are going towards filtering, we will need like some kind of filters. The idea here is, can we create filters which can compute these derivatives for us? So we'll call those derivative mask. And you can think about like it's pretty simple. For all those three terms which we studied like in the last slide, backward difference, forward difference, and central difference, we can actually represent those differences using these masks. All right, so this is for central, that's forward, and that's the backward. Now let's see how that's the case. So let's say if you have this derivative mask and you put this mask on these two values, that's how you perform filtering. We studied that in the last lecture, right? So what you will do, you will perform element-wise multiplication, and then you will just add those values. So it will give you like the negative sign to the first value. It will become -10, and it will remain 15 because it's just identity value 1. And then you can just add those two. That's going to give you 5. So essentially what it's trying to say is, if you use this as a filter and perform filtering using this mask on this function, then that's going to give you the first derivative of this function. So this will be the first location where you will place this filter, and then you will keep sliding towards the right. This will be the second location, and you will keep doing that. And essentially the output is going to be the first derivative. And the result, you can quickly analyze that when it's going to be no different than when you were just trying to take difference of these subsequent values, because that's what this backward difference is doing, this mask is doing. All right. Now that was one-dimensional function, and we can easily extend this to two-dimensional or three-dimensional functions. All right. So first, let's try to understand like what derivative will look like for two-dimensional functions. It's a little complicated, but not very difficult to understand. So if it's a two-dimensional function, then your domain will have two different axes, x and y. Right. So the first, the one-dimensional derivative was simple. You compute derivative, and again you will get a function. In this case, it's slightly different because you have two different axes, and we represent a derivative in two-dimensional in form of gradient vector. All right. And it's represented as like this inverted delta over here. This is symbol for gradient. So if you have to compute a gradient of a function which operates on two different dimensions, x and y, first of all, that will give you a vector. Okay, it's not going to be a single function. And that vector will have two different values. So this on the top, that's the first value. And on the bottom, that's the second value. I will explain like what these two values are. But let's try to understand like it's a vector with two different values. The first one is corresponding to one of the axes. The second is corresponding to the second axis. And in short, we also represent that as f subscript x and f subscript y. Right? So this is kind of, if you think about this at a high level, the first value is trying to compute the derivative in just x-axis, keeping the y-axis as a constant. And similarly, the second item over here, we are trying to compute the derivative in the second axis, again, keeping the first axis as constant. And that's exactly what we do. And this is called partial derivative. What we will do is, and it's defined using this symbol deba over here. So again, we just compute derivative of that function with respect to x. And we assume that the second axis y, it's constant. So that will give you derivative in x direction. And the second item is, again, you can compute the derivative. Again, with respect to y, you will consider x as constant. So these steps are simply like the way you compute derivative in your one-dimensional function. You will do exactly the same. And if you do it in 2 different dimensions, it's going to give you 2 different values. You will put those 2 values in a vector form, and that's going to give you the gradient vector. Okay, so that's one aspect of derivative in 2-dimensional. The second is the gradient magnitude, which kind of indicates how big the gradient is. All right. So the idea here is, again, you use these bars to represent it. Again, this is your gradient vector. And the idea is you're just computing the size of your vector. That's the standard formula we have seen. It's like kind of, you can say, L2 norm. You square the first value, you square the second value, you just add those and compute the square root. So that is called the gradient magnitude. And there's one more term which is associated with derivatives in 2-dimensional, which is called gradient direction. Because now you have 2 different dimensions and you are independently computing derivative in each of those 2 directions, which is fine. But then it's interesting to also see like which of these directions is more prominent. So which way the derivative is actually going. So at an intuitive level, if you think about if your derivative is, if your function is not changing in one of these directions, let's say y, it's almost 0. Then if the function is only changing in x direction, then the gradient direction will be in that direction, right? The x-axis. So the gradient direction gives you the sense of where the function is actually changing, where it's going. All right, so now using that definition of derivative in 2-dimensional, we can actually compute a derivative for images. And earlier I showed you the mask which we came up for just a 1-dimensional function. Here we have masks for 2-dimensional function. And you can see that it's just like an extension of what we saw earlier. So earlier the central mask was, central difference mask was -1, 0, and 1. In this case, we just extend it to like 3 rows so that we can use it to like operate in the images, right? So this is kind of a derivative mask which can be used to compute edges in x direction. And you can see that the values are changing as we are moving from left to right. So it's going from -1, 0, and 1. So this is going to give you edges in x-axis. And again, if you look at the filter of y direction, it's actually changing in y direction. It's going from -1 to 1. All right. So these are the masks which you can use to compute derivatives in 2 different directions. So this is kind of a 2-dimensional derivative, discrete derivative. So let's quickly run through this using this simple example. So in this case, the input is a 2-dimensional function, and we can consider this as an image patch. All right, so all these are pixel values. Now, this is the first position where we can put this kernel. So we are computing the derivative at this location. So let's first compute like derivative in x direction. And what you can do is just do element-wise multiplication and add those values. If you will do that, so all these values will be 0 because the central column is all 0. And all these will become -10. If you add those up, it's going to give you -30. All right, so let's try to collect those values. And this third column over here, it will be multiplied with all 1. And if you sum those up, it's going to give you 60. And if you just add up all the values, 60, -30 is going to be 30. And you have a normalizing factor here. So that gives you 10, which means that at this location, the derivative in x direction is 10. All right, which means the values are actually changing when you're moving from left to right. Similarly, you can compute the values like at all the other locations. The borders are all 0 because we don't have like values on the left. So right now you can just ignore those. All right. So one thing you can see at this location, the value of derivative is actually 0. Right? So if you think about what this derivative mask is doing, it's trying to find out if you move from left to right or in the x-axis in this input patch, then whether the values are changing or not. So that's what your derivative tells you, right? How much it's changing. And if you look at this particular section of the patch, all these values are 20. So the value is actually not changing if you move from left to right. So that's why we have a 0 here. All right. At all the other locations, for example, these 6 locations here, and you can see like the value is actually changing. You are going from like you were 10 and then it become 20, right? So the values are changing. Okay, so now let's go to the derivative in y direction. All you will have to do is use the second mask over here, which is again checking like whether the values are changing in the y direction or not. And this is the output. And if you look carefully at this patch, the values are not changing at all when you move like in the y direction. So all the columns, this is consistently 10, this is also 10, and all the last three columns are consistently 20. So if you move in the y direction, values were not changing. Therefore, you got like all 0, right? Now, those were like a standard mask to compute image derivatives. And if you run those masks over like standard, let's say grayscale images like this, these will be the output. And this is kind of giving you the magnitude at each location after computing derivatives both in x and y direction. Okay, so you can see that this is kind of giving a sense of what kind of edges are present in your input image. Okay, so this is like the horizontal derivative, this is the vertical derivative, and this is like a Laplacian operator. So don't worry about this now. We are going to go through this later on. This is kind of utilizing second order derivative, and you can see that it's actually much better than this these two results, which is using the single order derivative. Okay, but you can see like the simple mask which we just saw, like it was just like values -1, 0, and 1, right? Just using that mask, how you can easily compute edges in your input image. So that part is very, very exciting. Okay.